All right, on the agenda, now that we have a working definition of the Jones tensor and a means for relating that back to the local frame tensor, how do we experimentally access the tensor elements in the Jones frame? And that's the topic for today. And the first thing we're going to consider is just the general architecture, which we will then apply for different specific polarization conditions. The Jones tensor, as we mentioned previously, is a 2 by 2 by 2 tensor, and it connects the incident, and this is in the case of some frequency generation, the more general case, it includes second harmonic generation as a subset. It relates the incident polarization states to what is generated through the nonlinear optical process. And we can write this Jones vector. We can relate that back. Here it's shown in tensor notation. We can relate that back in vector notation, where we vectorize the Jones tensor through this linear algebra expression. And what we do is we take the two-element vector and transpose it to make a 1 by 2, and then multiply that, in this case, by itself, because A and B are equal in the case of second harmonic generation. And that makes a 1 by 4 product of the two incident polarization Jones vector elements. And then Kronecker that with a identity matrix, and that identity matrix then allows us to describe the horizontally polarized component in terms of these two terms, and the vertically polarized component in terms of these two incident polarization states, and therefore accessing all 8 elements in the Jones tensor. And we can describe this mess of stuff, which is really just a simple 2 by 8 matrix, by E. And we can use that notation to simplify things for the Jones tensor. All right, so if we plug and chug, explicitly put in omega 1 and omega 2 in this case, this is again for the most general case of some frequency generation, although for second harmonic generation, just set omega 1 equal to omega 2, and then everything else is good to go. This explicit evaluation, we get the same product of 4 that appears here and here when we do the Kronecker product with the 2 by 2 identity matrix, and then explicit multiplication by the Jones vector, the Jones tensor in vectorized form. My apologies. Yields this expression for the Jones vector of the sum in terms of the incident polarization state and the vectorized form of the Jones tensor. All right, so in the case of second harmonic generation, it's just the same thing backwards and forwards and upside down and to the right, except we've just explicitly substituted in the sum equaling to omega and omega 1 equaling omega A equaling omega B. So how do we then recover these from measurements of that as a function of that? And you can immediately see from this simple linear algebra equation that if we have 2 observables and 6 unknowns, and I say 6 because in the case of second harmonic generation, omega 1 is equal to omega 2, and so we have a 2 here, and we've contracted this down from 8 to 6 unique tensor elements. How do we recover these 6 tensor elements from these 2 observables? And the answer is you can't. No way you can do it because you have far more unknowns than observables. So there's 2 strategies. The first, increase the number of measurements. And the second is decrease the number of unique tensor elements. We can increase the number of measurements by recording the polarization state or the Jones vector of the detected beam for multiple different incident polarization states and stack this. Basically make this, instead of a 2 by 8, 2 by 6, make it a arbitrarily number n by 6, and then that way we can invert that once we use the tricks of linear algebra to recover the unique elements in the Jones vector, a Jones tensor in vectorized form. And before we do that, though, it really makes sense to think about how we might first consider decreasing the number of unique tensor elements. And one way to think about that is to use symmetry. So we realized in the previous discussion that we can describe in something that is locally uniaxial. We actually have far fewer than 6 unique elements. In fact, we have only 4 unique tensor elements with respect to the field of view. And if the system is aligned within the field of view, that we can't access this chiral term, which often tends to be weak and relatively small in general, and that leaves us with only 3 unique elements in the local frame. Now we still have to connect those back to the experimental observables and this matrix E, but we do it by just substituting, right? We can just take this vector here and plop it in there, and now we're going to multiply these two things together to reduce the number of free parameters we have to evaluate. And that gives you this expression right here, which is just the just substituting in this mess with XYZ and this first column excluded for this set of unique elements in the Jones tensor. And if we do that substitution, then you end up with this linear algebra expression, which actually is not that bad, right? We still only have 2 observables and 3 unknowns, which is unfortunate because we still can't invert it, but we're closer. We're closer. So we have a better shot at being able to isolate and recover these tensor elements from a smaller number of measurements of the polarization state of the detected beam. So that's the first step in reducing. Actually, I take it back because, clearly based on my ordering, that is the second step in reducing the complexity of the problem. The next thing we'll be discussing is the first, and that is how do we rationally increase the number of measurements, and how much information can we gain from increased number of measurements if we design the measurements appropriately. In other words, there's only so much information content available. How much is there? How do we access all of it? And what experimental considerations go into that decision making in terms of experimental design? And that's where we'll be heading next.